Welcome to the visit training session titled Utility of GOES Satellite Imagery in Forecasting and Nowcasting Severe Weather. My name is Dan Bicus. The main goal of this session is to understand the use of satellite imagery during severe weather events. For our learning objectives, we'll first look at assessment of model performance, how to gain confidence in particular model solutions with observational data. Then we'll look at air mass identification, identification of changes in the pre-storm environment, and finally, monitor the changing environment during the nowcast to warning decision-making time period. Note that we have these ordered approximately chronologically, where we go from about a day or two before the event to a few hours before the event to as the event is unfolding. So as we go down in this list here, the role of observational data becomes increasingly important. Now let's discuss our first learning objective, which is assessment of model performance. The goal for assessing model performance is to gain confidence in one model solution versus another for a feature location, say the 500 millibar trough, under the condition that at times the position error in the model may be carried along from the previous model run. So what you would do is compare the observational data with the NWP output to look at which model solution handles this more correctly in terms of the location of the feature. And this is a short-range comparison of model solution versus the observational data, meaning that we're looking in that 12 to 36, maybe 48-hour time period before the severe weather event. Now let's look at a case where we compare the 500 millibar height fields from various model solutions. First, we'll look at the GFS in green, the NAM in red, and the UK Met in cyan. These are all from the 0Z run on the 22nd of April 2007. And what we're doing here is overlaying the water vapor imagery that leads up to the morning of the 23rd of April 2007. And the idea here is that if a severe weather event was forecast for the afternoon of the 23rd in the plains, and we'll just be following the trough along here as it moves through the west. Now you can see over Nevada we begin to see some discrepancies in terms of one model solution being faster than some of the others. And what we'll do here is just look at this in a little bit more detail. So I'll stop this at a particular time and overlay the GOES 500 millibar winds here at this time right here. This is the GFS winds and heights. And we can see a decent agreement between the GOES derived winds here and the 500 millibar height field here, maybe a little bit further to the southeast. If we compare that with the UK Met, it looks like a pretty good agreement here in terms of the position of that 500 millibar low. And then finally, if we look at the NAM, you can see that there is a discrepancy here between the GOES 500 millibar winds and the position of that 500 millibar low. It just looks like it should be further southeast, in other words, faster than what the NAM is showing. And then finally, if we go a little bit later to 12Z, we can actually compare that with the RAOBS observations here at 500 millibars. And first, we'll go ahead and look at the heights. And we can see over Arizona, the Tucson Ob right here is 558 decameters. The GFS has it at 561, so maybe a little bit further to the southeast, and that agrees up here as well. 559 here at Reno. Looks like it should be a little bit further to the southeast. That was the GFS. Now let's next look at the UK Met here. And here it looks like a pretty good agreement. At Flagstaff it agrees pretty well at 558. Down here we do see some discrepancy at 565 versus about 560 in the model, so it looks like the UK Met here is a little bit too far south with it, but in terms of its eastward progression it looks to be pretty good. And then finally with the NAM, comparing that with the 500 millibar RAOBS here, you can see actually a pretty big discrepancy where it has 563 here at Flagstaff, so it's definitely further southeast than what's being shown here in the NAM. And finally, by looking at the analysis for that time period, we can actually see here that the NAM is too slow. So basically what we looked at here in review is we compared the GFS, the NAM, and the UK Met, and they had some different positions here that were carried along from previous model runs. I just happened to choose the 0Z run on the 22nd. It also showed up in some other runs. And what it showed here is that the NAM was clearly an outlier. It's slower than the UK Met and the GFS. So when looking at model fields for the severe weather event forecast over the plains for that afternoon, just keep that in mind, that the NAM would be an outlier here in terms of having less confidence in that model solution versus the others. The next learning objective is air mass identification. Sometimes there's signatures in the visible satellite imagery that can be used in tandem with surface and upper air data to delineate different air masses and boundaries. In this GOES visible imagery, we see this boundary that's oriented from northeast Nebraska towards southwest Minnesota. South of that boundary, we have unstable cloud streets, which are oriented parallel to the low-level flow, and that's what's indicated here with the surface wind barb. And then to the north of the boundary in the unstable air mass, we have these stable wave clouds, and these are oriented perpendicular to the winds at inversion top level, which is depicted by this barb right here. For this case, we'll be looking over Iowa. This is the GOES visible imagery from 11 May of 2000, and what we're going to highlight here is the development of stable wave clouds as well as unstable cloud streets that are developing here across Iowa. And if I overlay the observations here, you can see unstable cloud streets developing over central Iowa, and just to the northeast of that you see some stable wave clouds. Now what I'll do here is just stop this near the end of the loop and analyze the various boundaries that we have. First of all, we have a surface low, it's just about right here, with a warm front extending northeast of the low, and then to the southwest of the low we have a cold front. Just east of the low we have the stable wave clouds, and then south of that we have these unstable cloud streets, which are oriented parallel to the low-level flow here, which is southwest. And then in between the two, we would have this boundary right here. So the area we would key in on in terms of potential for convective initiation a little bit later would be just east of the low, right along that boundary between the unstable cloud streets and the stable wave clouds. And we can see quite a bit of convergence in that vicinity in the observations here, just out ahead of the low. Now let's look at what happened. Here's the boundary we had been following, and we go to a little bit later, we can see that boundary moving towards the northeast and towering cumulus forming along that boundary just east of the low, right in here. And if we go ahead and animate the loop, that's where the convective initiation takes place. So here in review, we utilize the GOES visible imagery along with the observations to pinpoint where convective initiation would occur. Our next case takes place in Ohio and Pennsylvania, and again we're going to analyze the various air masses and boundaries for this particular event. Now, the first thing we'll notice here is this north to south oriented line of convection that moves off towards the east and northeast here across New York and Pennsylvania. And behind that we see a front further to the west and impinging on the western Ohio and into Michigan by later in the day. So in between that we have our warm sector here, mostly over Ohio and western Pennsylvania, and points to the north here. Now notice the dew points are actually the highest just out ahead of this cold front across Ohio and then extending further to the northeast. One other thing I wanted to point out is, I'll stop this loop in the morning hours, and you can see stable wave clouds here in the Cleveland area, generally in this vicinity right here. And then as we go through the daytime heating, we can actually see a transition from stable wave clouds to unstable cloud streets. Here we see the unstable cloud streets that are oriented parallel to the low-level flow, which is out of the southwest here. And then we get to the last time, and we can see our cold front back to the west right here. And in this vicinity, right around Cleveland, you can see indications of another convergence line, a prefrontal trough line. You can see enhanced cumulus developing right around Cleveland. And you can also see indications of convergence if you look at the surface winds, where you see winds backed more out of the south and southeast across northwest Pennsylvania, and then further to the west here, they're more out of the southwest. So we have a cold front, a prefrontal convergence line, and we see indications of a unstable air mass here across Ohio, and then as you get well to the east here across Pennsylvania, you see more stable wave clouds. So we have our warm sector defined here and the various boundaries where we might expect convection later on. Let's take a look and see what happened during this event. You can see thunderstorms initiated just east of Cleveland and moved off to the east. Note this area just east of Cleveland. I'll go ahead and stop the loop here, where we see this region of enhanced cumulus in northwestern Pennsylvania. As I roll through the loop again, that's actually an area of an enhanced instability, of a more favorable near-storm environment, and that we also have more backed winds in here, southeasterly flow, and then obviously the convergence coming in along that prefrontal trough, and a number of tornadoes that developed in that area, F3, F4, and even an F5 tornado that moved from northeast Ohio into northwest Pennsylvania. Further to the south, most of this convection couldn't get going until the cold front finally came through. So it was that area further to the north along that prefrontal boundary that we were talking about where most of the significant activity took place here. And then finally later on we see larger aerial coverage if thunderstorms break out along the cold front. Our next learning objective is identification of changes in the pre-storm environment. One of the major reasons we see changes in the pre-storm environment are due to mesoscale convective systems, or MCSs. Monitoring MCS activity for potential effects on later convection is particularly important because this is an area where NWP output can struggle. This is where forecasters can have significant value added to the forecast by monitoring observational trends to understand the consequences of an MCS on future convection. The steps you would take to understand this would be first, identify regions that are stabilized by the outflow boundary from the MCS. Second, identify the boundary between the stable air mass that we identified from the previous step and the potentially unstable air mass. And then finally, monitor for future convective development. Not only convective initiation along the MCS boundary, but also any interaction that takes place between a new storm and the MCS boundary. Let's take a look at an example where we see an MCS that originates in central Kansas, puts down an outflow boundary that moves to the southwest, and it has a pretty big effect in terms of potential convection. The first thing we notice here is the various air masses, like we've been identifying earlier. I'll go ahead and stop that midway through the loop, and we can see stable wave clouds in the region left behind by the MCS outflow boundary. Here's that MCS outflow boundary that's moved to the southwest, and we can see the unstable cloud streets in the warm sector just south of that, where we have the southerly flow. And then finally we see thunderstorms initiate along the MCS outflow boundary, and in some cases the thunderstorms actually move into the region where the stable air mass is, and these storms become more elevated in nature. And in other instances, these storms move along the MCS outflow boundary, such as the one that I'll highlight right here. This one right here moves along the MCS outflow boundary, so it has access to the unstable air feeding in from the south. It also has the advantage of riding along a boundary, and this particular storm had a number of large hail reports, all the way up to 4¼ inch in diameter. So by monitoring the effects of the MCS that we had earlier, the outflow boundary that it puts down, and then the different air masses that we see, and also looking at the storms and considering the storm motion as well. Are they moving towards the stable air mass, or are they moving along the boundary? And in the case where they're moving along the boundary, the storms remain intense for a longer period of time. Now let's look at the effects of an MCS over a larger scale. We'll start with the 500 millibar heights and winds overlaid with the Cape, which is shaded here. You can see a closed low over Wyoming, and that's forecast to move towards the north during the day. And across the plain states, you can see a broad area of southwest flow. There's actually a dry line here. Just out ahead of the dry line, we have our warm sector. So let's look at our warm sector here in more detail. I'll bring up the surface winds along with the dew points. And you can see this dry line, which affects dew points into the 60s and 70s up into Kansas and Nebraska here. And also notice the Cape values right around 3,000 to 3,500 here in eastern Nebraska, values above 3,500 to 4,000 in Kansas, and further south down here in Oklahoma as well. So a fairly large warm sector here where we have pretty good instability values from South Dakota and points further south here. Now let's compare that with the NOM 12 forecast. Again, this is 12Z, and we're just going to overlay the dew points and the winds here. And it looks very similar to the GFS here, which is showing this warm sector across Kansas, advecting moisture into Nebraska here during the day. And by the time you get to 0Z, it actually looks very similar to the 12Z run of the GFS that we just looked at. Cape values here around 3,000 in Nebraska, and higher values to the south, 4,000 or so in Kansas, and further south here in Oklahoma as well. So the GFS and the NOM both show a pretty large area of warm sector here out ahead of the dry line, with Cape values around 3,000 to 4,000 in Nebraska and Kansas. Now let's compare that to what took place during the overnight period. So what took place up to that time of those 12Z runs that we just looked at. And what I'll do is speed up the loop here, and you can see this MCS that developed in the evening hours of the previous day and went through the overnight hours, pretty significant MCS across Kansas into Nebraska, and actually started across northwest and north central Oklahoma as well. So as you might suspect, that would have a significant role in terms of how much instability might develop the next day, how much moisture will make it back into this area that we were just looking at in terms of the very unstable air mass we were looking at. For comparison purposes, here's the 0Z run of the GFS, the QPF, and you can see the majority of the QPF going towards the north here through Nebraska, and not a whole lot over here in Kansas and further to the south here. So it really missed out on a large portion of this MCS over here in Kansas, southern and eastern Nebraska, and also north central Oklahoma. If we compare that with the NOM, it looks pretty similar. It does have the majority of the precip on this corridor here moving towards the north. It does have a little bit more to the south here in Oklahoma, but you can see it's still missing a fair portion of it here across Nebraska and into Kansas and north central Oklahoma here as well. So in summary here, we had a pretty significant looking MCS during the overnight hours, and now that the magnitude of the Cape might be a big question mark here. Let's go ahead and look at that next. Here's the surface-based Cape analysis from the SPC Mesoanalysis page, and you can see a very different picture from the NOM and GFS that we were looking at earlier. Remember, the NOM and the GFS had 3,000 plus joules per kilogram here in eastern Nebraska with higher values to the south, and we look at the analysis here. This is the 1,000 line in eastern Nebraska. The 2,000 line just noses up into central Nebraska, and the 3,000 line is much further to the south, near the Oklahoma-Kansas border. So considerably less Cape than what was forecast by the 12Z run of the NOM and the GFS. Just for comparison purposes, here's the ML Cape, and you can see a pretty similar story here with 1,000 up here in Nebraska, and then the 2,000 line is actually near the Kansas and Oklahoma border with higher values further to the south. Now let's look at the GOES visible imagery and see what actually happened. First of all, you notice no storms here over Kansas, and then actually a stable look to these clouds, some stable wave clouds across Kansas, indicative of that MCS that had just gone through earlier. Further to the north here in Nebraska, we see some storms that do get going along this dry line right here, but they appear to be lacking in Cape. As we suspect, we just saw the Cape analysis only showing about 1,000 joules per kilogram, and consistent with that, the only severe weather report on this day in the state of Nebraska was a 3/4 inch hail report up here, so quite a bit less severe weather than what you would have if there was more than 3,000 joules of Cape here. So the only two areas where there were severe weather on this day was down in Oklahoma, and we'll look at that in more detail here in the next slide. And then finally up near the low itself, the 500 millibar low that we were looking at. Remember, that was situated in Wyoming, moving towards the north. So this is an environment that's quite a bit different than further to the south here, and that our lapse rates are quite a bit steeper. We have colder temperatures aloft here, so even though the dew points are somewhat lower, the lapse rates are substantial up here. And you can see some storms going up that produce tornadoes here across central South Dakota and points to the north here as well. So next, let's look at what happened down here in Oklahoma. Okay, not much in the way of severe weather across Kansas and Nebraska here because of the MCS, the stabilizing influence of the MCS. But if we go further to the south here, we can see in the close-up of the visible imagery here over Oklahoma, the MCS outflow boundary pushing towards the southwest, and as it intersected the dry line, we saw convective initiation take place right around here. And if we look just east of that, we can see stable wave clouds on the stable side of the outflow boundary here, and that's supported by the observations here as well. And then if we look south of the MCS outflow boundary, we can see unstable cloud streets here, and that will be feeding towards the north, towards some of these storms. And if we look at what happened here, the first attempt at convective initiation actually moved off towards the northeast into that more stable air, and that storm became more elevated in nature. And there was actually an outflow boundary from that initial storm, put down another outflow boundary, which caused additional convective initiation to occur. And then finally, down here on the third try, in terms of the multiple outflow boundaries that interacted with the MCS outflow boundary here, finally got a storm that could really get going here, take advantage of the warm sector feeding into that storm, as well as the fact that it's riding right along the convergence boundary there. And we got a tornado report right around here in northwest Oklahoma. Our next case takes place in July of 2000, so we're switching from springtime to summertime scenario here. We'll start off with the 500 millibar wind. This is from the Eta at the time, and the Cape is shaded. And we'll advance through the day. Our forecast area here is northeast Colorado, this area here, and we can see that aloft we have southwest flow around 25 to 30 knots or so, and the values drop off dramatically as we move off to the east here. Now let's go ahead and bring up the MSLP along with the surface winds, and we can see that we have a low here over northwest Kansas in the morning, and as we work our way through the day, that low is forecast to deepen, and by the time we end up at the 12-hour forecast here valid at 0Z, you can see this broad low to the west, which puts our forecast area in south to southeast winds. Now note the main Cape axis here is northeast of our forecast area here. So let's look at that in a little more detail by bringing up the dew points and looking at the evolution of the moisture through the day. At 15Z, we can see higher dew points here around 65 to 70 in northeast Colorado. By 18Z, we can see dew points in the mid-60s here. But then what happens next here, you can see those dew points decreasing by 21Z, and correspondingly the Cape decreasing. And then finally by 0Z, we can see the dew points down into the 40s here. So what happened if we look at the temperatures during that same time period here, you can see the temperatures in the 80s to around 90 by 18Z, and then really warming up into the upper 90s by 21Z. And by 0Z, you can see temperatures 95 to 100 in our forecast area here. So what we're looking at is the Eta mixing out the dew points here with the temperatures really increasing into the upper 90s on this day, which keeps the main instability axis here further to the northeast and to the north of our forecast area. Now that's the forecast for the morning. Let's go ahead and continue to look at observational data and see how this forecast pans out as we move through the day. Now let's look at the visible imagery from the morning through the midday hours, and you can see a few clouds burning off here in northeast Colorado, temperatures warming up into the 80s, and dew points fairly high in the 50s to 60s here in northeast Colorado. So far so good in terms of the forecast through the midday hours here. However, one thing to keep in mind is this MCS that we see over Nebraska, and you can see outflow from that MCS pretty easily here on the southwest flank of it, moving towards the southwest here. So that's something to keep in mind as well. Now let's look at the GOES-IR imagery, the 10.7 micron imagery here. And it turns out that the IR imagery is very good at seeing a difference between a moist air mass, such as this area and here. The very light colors represent cooler brightness temperatures, and that's the more moist air mass compared to the drier air mass that we see further to the west here. Those are warmer brightness temperatures corresponding to the drier air mass that heats up faster here further to the west. So if we keep that in mind and follow the MCS boundary here that tracks from southwest Nebraska into northeast Colorado, you can actually see the leading edge of that outflow boundary as it moves into northeast Colorado. So next, let's look at that in the visible imagery. Now let's look at the GOES visible imagery, and we can follow that MCS as it moves off to the east with the associated outflow boundary moving through southwest Nebraska. You can see the leading edge of that outflow boundary quite well with the cumulus along it as it moves into northeast Colorado, and then finally through later in the day some of that cumulus goes away and it becomes less easy to see here. Note that a thunderstorm goes up along the southern edge of this outflow boundary here in southwest Nebraska. Remember, the flow aloft here was somewhat lighter as we went off to the east here. Now let's focus on our attention over here to the west, and you can see thunderstorms initiating in Wyoming and western Nebraska. Remember, the temperatures there were very warm in the 90s with dew points in the 30s and 40s, so we had a hot, dry air mass where these thunderstorms were going up. And then note this thunderstorm as it moves into south-central Nebraska. It takes on a different appearance, and also the storm motion goes from a more northeast storm motion to moving more towards the southeast or even south. So let's look at that in a little more detail here. And what I'll do here is just go to the time where this thunderstorm begins to have an overshooting top right here. And then on the western flank of the storm, we see these towering cumulus that form. These are actually towering cumulus that form above an invigorated RFD. And we'll talk about these in more detail a little bit later in this session, but for right now, just think of it as a storm that's undergoing intensification when you see these towering cumulus that form above an invigorated RFD. What's happening is this thunderstorm has interacted with the outflow boundary from the MCS, so now it's dealing with much higher dew points than it had been previously, and therefore higher CAPE values here. So this thunderstorm has a much more favorable near-storm environment to work with. It's intensifying, and shortly after this it went on to produce a F3 tornado here in northeast Colorado, as well as some softball-sized hail. Next, let's look at the radar reflectivity associated with this here. Here's the radar reflectivity, and the first thing to notice is the outflow boundary shows up here as it's moving through northeast Colorado. And note the dew point right here at Akron, where we go from dew points in the upper 40s to the mid-60s. So we've introduced this warm, moist air mass into the region, and also consider the effects of elevated heating as well, where elevation increases dramatically as we go from Nebraska over here into northeast Colorado, where the elevation's around 4,000 feet or so. So we're looking at CAPE values here around 4,000 joules per kilogram, and obviously that's significantly different than what we were looking at from the ADA forecast for this morning. Very high instability values for this storm to work with here. So if we're looking at this storm right here, moving to the southeast, a couple effects to keep in mind in terms of explaining its storm motion. First of all, the storm is moving along that MCS outflow boundary, which is oriented like so here. And also, we have the effects of a right-moving supercell, the dynamical effects. So the storm went on to produce an F3 tornado as well as softball-sized hail. And in summary, this is very different than what the models were showing from that morning. And by following the observational data, the trends that we see in the MCS, where that outflow boundary is going, we're able to get a handle in terms of where the severe weather event will occur, and this is a fairly significant severe weather event as well. For our next case, we'll be forecasting for northwest Kansas. And note in the water vapor imagery leading up to this event we have a trough over Idaho and Montana here, which puts a broad region of southwest flow here across the plains and including our forecast area. Also note the MCS activity. We have multiple MCSs through Kansas extending up into Nebraska. Let's look at the NAM 12Z run. This is the Cape, which is shaded, MSLP, along with the winds. And it seems to have some indication of the more stable air mass associated with the MCS in this corridor here, with more unstable values to the west here. Now, if we march through the day, we continue to see that same pattern with more unstable air to the west, and we get into the afternoon hours, and we can see the low taking shape here by 0Z in the vicinity of eastern Colorado, and a dry line just out ahead of that low, with pretty good instability forecast here. Cape values around 3,500 joules per kilogram or so in northwest Kansas. Fairly strong winds out of the south-southeast as well. So that area just northeast of the low appears to be an area to watch here in terms of favorable low-level dynamics. Next, let's look if there's any support at upper levels here as well. Here's the water vapor imagery from the late morning through the early afternoon hours, and what I'll do is speed up the loop here and watch this area right here in south central Colorado, this darker region here, and by the time we get to the end of the loop, it's right about here. That's actually a shortwave that's moving around the trough here, moving towards the northeast, and actually heading right towards our forecast area here in northwest Kansas. It is a fairly subtle feature here, so let's go ahead and overlay the 500 millibar heights along with the vorticity here, and you can see that that tends to be supported here as well. That it appears there's a short wave in that area, and it's moving towards northwest Kansas. Now let's look at the visible imagery and analyze the various air masses and boundaries. First of all, here's that MCS that we had been analyzing earlier, and we can see an outflow boundary emanating out away from that MCS towards the southwest or the west. Notice that we have stable wave clouds here during the morning hours, and we see a transition from those stable wave clouds to unstable cloud streets as we go through later in the day. And interestingly enough, we see even some of these particular lines here that were associated with these stable wave clouds early in the day with daytime heating actually take on the appearance of a unstable cloud street, but they're still there, which is pretty interesting to note as well. Now let's go ahead and overlay the observations, and what we have is a fairly narrow warm sector here bounded by the dry line to the west and the outflow boundary to the east, so it looks something like this, and it will be shrinking as we go further to the north here. One other thing to note is the winds. Note the winds here to the south, very strong, 30 knots gusting to about 35 or so down here. And then just to the north of that, we see the winds are somewhat less. Disregard this right here. But that could help explain the reason why we see this line right here that transitions from the stable wave clouds to the unstable cloud streets, yet you still see it there because we have some sort of speed convergence between the stronger winds down here and then somewhat lesser winds just to the north of that as well. Now let's go ahead and follow what takes place. We'll start with the first signs of convective initiation here, and you can see some storms going up here, some going up here, and then some going up here. We'll talk about these three areas. First of all, this one right here is going up right along the edge of the MCS outflow boundary, so storm motion would take it this way towards the northeast fairly quickly and become more elevated in nature, whereas these storms in here have a fairly narrow corridor of warm sector to work with before they would eventually move off towards the northeast and become more elevated in nature, whereas the southernmost storm down here would have a long time in the warm sector and also the potential of interacting with this MCS boundary before it actually intersects with that boundary as well. So let's go ahead and animate the loop, and we can see that the storm that persists for the longest here is that one that has that long time in the warm sector through here, and then it actually interacted with the MCS outflow boundary and produced some significant severe weather, which we'll look at in the radar reflectivity loop next. Here's the radar reflectivity loop from the Goodland radar right here, and you can see our storm of interest initiated right in this area, and then moved to the northeast for a little while, but then it turned to the right, and even maybe a little bit east-southeast for a short period of time before eventually moving off to the northeast again. And what we're seeing is a storm that's undergoing intensification and dynamical effects of being a right-moving supercell, as well as effects of propagating along that MCS outflow boundary for some period of time before eventually moving off to the northeast again. This particular storm had F2 tornado and golf ball size hail associated with it. So by looking at the various air masses, the boundaries that we were looking at earlier, recognizing that particular storm would have a longer residence time in the warm sector, giving it a better chance to intensify and really get going, we could use the observational data in that way to really hone in on which storm was likely to be one of the more nasty severe weather producers here on this particular day. For this case, we're going to follow this cloud feature that we first identify here in southeast Nebraska in the late morning hours as it moves towards the northeast. We go ahead and let this loop, and you can see that moving towards the northeast through Nebraska and into Iowa. And as it moves along, you can see there's enhanced cumulus with that pretty much through its whole time as it moves through the Omaha area into Iowa, and then finally as it moves into this area where we have convective initiation takes place coincidentally with this feature here. If we look at the surface observations tracking that along, you can see that just behind this feature the winds veer and gust stronger as that just after that feature goes through the region here. And then finally, the other thing I did here was just track this with the speed tool in AWIPS and found that this feature was moving at 54 knots. Now next I'll look at a sounding that was launched at Omaha at 18Z, and you can see that was fortunately right at the exact time and place that that feature happened to go through here. And the other thing I'll say here is that I used the cloud height algorithm in AWIPS to determine the height of these clouds, and they were right around 700 millibars or so. Here's the Omaha sounding at 18Z as that feature of interest was moving through the area, and what we can see here is the winds at 700 millibars, which corresponds to the cloud height that we just looked at here, right around 50 knots. And that corresponds well with the speed of the cloud element of interest as well. Now let's look at the 700 millibar isotax along with the available profiler data, and you can convince yourself pretty easily, if I add the Omaha 700 millibar observation on here, that this was a mesoscale jet streak, the feature that we've been analyzing here, moving through the area, and helped to cause a very favorable near-storm environment for this storm that struck north central Iowa here. And by monitoring this with the satellite imagery and then getting corroborating evidence from profiler data, the 18Z observation from Omaha, and if there's any other available data such as ACARS data, model analyses, go ahead and use it and just continue to monitor that and keep in mind that's a red flag in terms of an area to keep an eye on for monitoring very favorable near-storm environment. Here's another example of supporting data for that particular case that we're looking at over Parkersburg, Iowa. If we go to 15Z here, this is the NOM 500 millibar heights and vorticity. We see the first indications of that mesoscale jet streak right here in southeast Nebraska, and we can track that along through the Omaha region, and then by 21Z up into the region where we saw convective initiation occur. So again, look at as many data sets as possible and try to understand where this is coming from, and again, just keeping a red flag on it in terms of monitoring this very carefully and knowing that it's associated with a very favorable near-storm environment. Our last learning objective will be to monitor the changing environment during the nowcast to WDM time period. Now let's look at an example here to see what I mean by monitoring the changing environment. So here's a boundary right here across southeast South Dakota, and a little bit after this time period we see a thunderstorm initiate along that boundary, and again we have our stable air mass to the north of that, unstable cloud streets to the south of that here. So this thunderstorm goes along for a little while and then it actually dissipates. We note that by the loss of the overshooting top here, as well as the anvil cirrus becoming more opaque in time here. But what happens is it puts down this outflow boundary on the west side of the storm. That intersects the old boundary that we were talking about earlier, and a new thunderstorm goes up along the intersection of those boundaries, and it goes on to produce a significant tornado. This is a very large tornado that went through Manchester, South Dakota, and this is what I mean by short temporal and spatial periods here, that where you're monitoring very fast-changing environment here, but very important changes taking place. In this particular example, a thunderstorm that persists for a period of time, and then it dies, but it puts down an outflow boundary that intersects another boundary here, and it goes on to produce a significant severe weather event. Here's our next example of monitoring a changing environment. And what I'll do is go ahead and start the loop, point out an MCS that was just offshore from the north coast of Florida here, moved across the northern portions of Florida, and you can see for the most part it stabilized the area as it went through. However, there were a few places where it actually enhanced the thunderstorm potential, and what I'll do is go ahead and point those out. First we'll go early in the loop here, and note this area right around here where we have the southern end of the MCS outflow boundary interacting with the sea breeze front right here. And what happened is a waterspout moved on the shore and produced a tornado right along the coast in this vicinity. And then the other area to watch is over here where the sea breeze comes on shore here and interacts with the outflow boundary from that MCS, and it actually produces some severe wind reports in this vicinity here. Eventually the MCS outflow boundary wins out and stabilizes the area as it moves through. One more example over Iowa and Wisconsin. Notice this MCS in Wisconsin, and behind that we have outflow boundary, and that's pretty well indicated by these stable wave clouds that you see through northeast Iowa. And then to the south of that we can see a boundary, and what I'll do is stop the loop at that time, and you can see the boundary between the stable wave clouds in this area. Here's the boundary, and then what we have to the south of that is unstable cloud streets. Bring up the observations, and you can see pretty high dew points and southeasterly flow here on the warm side of the boundary. And what happens is a thunderstorm goes up along that boundary just northeast of this station right here, and produces a brief tornado before it eventually moves off to the east, becomes more elevated in nature, and then quickly dies out after that. So this is another example where we see the influence of an MCS leaving a MCS outflow boundary. A storm comes along and interacts with that boundary and produces a severe weather report from that. Next, we'll consider cloud features that may be detected in the vicinity of severe storms. What we're looking at in this schematic is what you might see in a visible satellite image of a supercell with an overshooting top above anvil cirrus. Here's the edge of the anvil cirrus that we see here, the flanking line right here. And then up here, or usually west of that, we have our lines of towering cumulus that form above an invigorated RFD. And then east of that, or down shear of the flanking line, are the inflow feeder clouds that form within converging inflow near the strongest updraft. And what mechanisms cause these various clouds to develop and how they relate to supercell behavior is an area of research. However, what we know at this time is that when you see these features, just know that the supercell is undergoing intensification. Also, there's numerous reasons why you might not be able to see these features, such as intervening anvil cirrus from nearby storms, high-level cirrus over the area, nighttime, goes east versus goes west, viewing angle, and so forth. Just know that when you do see these features, that the thunderstorm is going through intensification. Now let's talk about the inflow feeder clouds, the feature that we see just downshear of the flanking line. And a recent study was done in which they looked at 131 storms and looked at the presence of inflow feeder clouds in severe weather reports within a minus 30 to plus 10 time-minute time period. Here's some of the results that they found from that study. First of all, like I said before, not necessary for severe weather occurrence. Treat this like the enhanced V signature. Just because you don't see the signature doesn't mean that severe weather is not happening. Feeder clouds are an indication that a storm is rapidly intensifying and may produce severe weather soon thereafter. And here's the key of what they found from the study. If inflow feeder clouds are observed, there's a 77% chance of severe weather within a 30-minute time period. And then if you combine that, the observation of inflow feeder clouds with the mesocyclone detection from the MDA, then there's an 85% chance of severe weather within 30 minutes. So keep these numbers in mind if you're on the fence in terms of making a warning decision-making judgment on a particular storm. And if you do see the inflow feeder clouds, think of these numbers. Now let's look at an example of what these signatures look like in the visible imagery. First of all, the inflow feeder clouds. We'll look at this thunderstorm that's going up here in Minnesota. We can see a nice outflow signature on the back side of the storm here. And then on the south side of the storm, we see the inflow feeder clouds. So what I'm going to do is just stop it and go to the right time where we see the inflow feeder clouds. So we're talking about this feature right here. These are the inflow feeder clouds that we see associated with that storm. Now note that some of these other storms up here may have that as well, but we have intervening anvil cirrus from nearby storms, which may prevent us from seeing it with the other storms. So the best time to look for these is either early in the convective development or with a storm at the south end, the tail end Charley storm. This is that you'll be able to see it sometimes in this type of scenario. Let's look at another example of inflow feeder clouds. First of all, notice this MCS. It's moving through Oklahoma, leaving this outflow boundary that's oriented like so here. And what I'll do is stop the loop and look across southwest Kansas at this developing storm in here. And now as we go a little bit later, we see indications of inflow feeder clouds right here. So we have inflow feeder clouds associated with this storm, and at 21:58 there was an F3 tornado with this particular storm and 2-inch diameter hail. Now remember, this is riding right along that MCS outflow boundary, so it's taking advantage of convergence along the boundary and that unstable air feeding into this particular storm right here. Then if we go a little bit later, we look at the storm scale features. We continue to see the inflow feeder clouds in here. On the back side of the storm, we see this outflow region right in here. And we continue to see that persist for a while until finally, by about this time, we see the outflow pretty much taking over here. So this storm becomes more outflow dominant. However, the next storm to the south here begins to take on interesting characteristics. First of all, let's go a little bit later here. And you can see indications here of inflow feeder clouds beginning to go into this storm right here. Notice, though, as we go early in the loop, that there was a pre-existing cloud field in this area in the Texas Panhandle, and we get the storm as it moves into this region here. It actually had a combination of inflow feeder clouds along with the existing cloud field in this region, and what you'll notice here as I go back and forth in the loop is these clouds are racing into the storm here. So let me go ahead and let the full loop go through here, and you can see the inflow feeder clouds initially with that storm in southwest Kansas and the Oklahoma Panhandle, and then later on you see it again with a storm in the eastern Texas Panhandle, and that particular storm had a tornado and golf ball size hail as well. And the unique thing about that southernmost storm was it was an area where there was an existing area of clouds already, so we had this combination of inflow feeder clouds and an existing cloud field, which you may see sometimes as well. Next, we'll look at a combination of the visible satellite imagery along with the radar reflectivity from the Rapid City, South Dakota radar site. And if we see this storm coming into eastern Wyoming here and moving towards the South Dakota border, here it is depicted on the radar reflectivity. And what I'll do is just advance along here until we see the first indications of inflow feeder clouds. And we see that right here at about 2145 associated with this storm. And you can see how it looks with the radar reflectivity at the same time here. Go a little bit later, you continue to see that signature for some period of time, and then it goes away by this time right here, by 2215. And we go a little bit later, and it comes back again here at 2225. And then a little bit after that, we get a tornado report at 2234. And you can see we have the inflow feeder clouds present at this particular time here. And then soon afterwards, they pretty much go away again as the storm becomes more outflow dominant. So in review here, we looked at a storm that was experiencing inflow feeder clouds at various times, and you can see in the radar reflectivity loop the corresponding images where the storm looked particularly intense at those times as well. And in this particular case, there was some 9 minutes lead time in terms of before that tornado report. Now, that's for this particular case. You should just be thinking of the storm undergoing intensification when you do see the inflow feeder clouds on the visible satellite imagery. Now let's switch gears to the towering cumulus that form above an invigorated RFD, the signatures that we looked at earlier that form on the upshear side of the flanking line. And to illustrate that case, we'll go back to our July 5th, 2000 case that we looked at earlier that affected northeast Colorado. What I will do here is just zoom into this area, and you see these thunderstorms that moved into this region where, recall, the MCS outflow boundary had pushed into this region, made for a very unstable air mass. And once that thunderstorm moved into that region, you can see it showed some signs of intensification in terms of the overshooting top. We also see the storm move more towards the southeast, whereas previously it was moving towards the northeast. And finally, we see these towering cumulus that form above an invigorated RFD. So when you see this in the satellite imagery, think of a storm that's going through intensification. Here's another example of towering cumulus that form above an invigorated RFD, and you can see it with this particular storm that's moving towards the south here across eastern Colorado, and near the end of that loop you can see the towering cumulus that form above an invigorated RFD. Let's go ahead and stop that and focus in on particular times right here. This is the signature you would look for in terms of the towering cumulus that form above an invigorated RFD. And when you see that, think of a storm that is undergoing intensification.